How does a computer magically shrink a giant 3D data object, mail it across the world, and grow it back to full size? Today, we are stepping inside a server's 3-story post office to see exactly how code is packed and shipped across the internet. If you crack open a standard server rack and look at the software running inside, you'd find a bustling, highly organized 3-story post office. Computer scientists have a specific name for this entire operation. They call it Remote Method Invocation. That is a dense phrase, but it describes a simple protocol. It is the official set of rules a client computer uses when it needs to call upon a piece of software that lives far away on a distant server. To pull off this long-distance communication without errors, the software architecture is divided into 3 distinct layers, working exactly like the floors of our imaginary post office. The goal of this setup is to hide the thousands of miles of cables between machines. When the system works, the remote computer feels like it is sitting right there in the exact same room as you. At the top floor is the Stub and Skeleton Layer, acting like a front desk clerk that intercepts client requests. Once received, requests move to the middle floor, the Remote Reference Layer. This sorting room uses network addresses to find the exact destination server. By intercepting the request and attaching the exact destination coordinates, these top 2 floors act as the brains of the operation. They figure out what the client wants, aim it perfectly, and send it downstairs. But before we can actually mail anything, we run into a physical limitation. Imagine trying to shove a massive, fully assembled toy robot through a tiny, flat network cable. It simply will not fit. To solve this packing problem, the server uses a Bitrel shrink ray powered by 2 processes, serialization and marshalling. This architecture diagram shows the technical process. First, serialization flattens the data. Then, marshalling transforms that bulky memory structure into a single file stream of bytes, dissolving the object into a simple string of 1s and 0s ready to travel. Without this translation step, heavy software objects would be permanently trapped on their home computers. They would have no way to move through a cable to share their capabilities. Now that we have a neatly flattened stream of data, we can take it down to the basement. This lowest software level is the transport layer. Think of it as a busy underground garage packed with delivery trucks. The transport layer handles the actual physical connectivity. It uses real internet protocols like TCP/IP to push the data out of the machine and into the outside world. By successfully making it to the transport layer, the software has crossed a massive boundary. It has bridged the gap between abstract computer code and the physical wires of our real world. Our flat data stream zips across the country and finally arrives at a completely new server building. Looking back at our diagram, we see the destination server uses a process called unmarshalling. It reads the flat byte stream and perfectly inflates it, rebuilding the 1s and 0s back into a fully functional software object in the new server's memory. Because the unpacking was successful, this destination computer can immediately interact with the new object as if it had created it locally from scratch. Our object smoothly dropped through the front desk Stub and Skeleton Layer, navigated the remote reference sorting room, and hitched a ride out of the transport layer. It was the digital shrink rays of marshalling and unmarshalling that made this physical journey across the internet possible. Next time, we will build a smart digital toll booth when we explore object middleware patterns like the factory, adapter, and interceptor. Thank you so much for watching.